What's up, guys? This is Jahangir from Emporium, and today we're going to be talking about buffer solutions. We're also going to be defining what buffers even are and how to calculate the pH when you're using a buffer solution. So let's start off by actually defining what a buffer is. So a buffer is something that resists pH. So I'll put resists pH changes. So a buffer just resists any drastic changes to pH. Like if we added a strong acid, then it will maintain its pH to the point where that strong acid doesn't lower the pH significantly. And if we add a strong base, a buffer will basically keep that pH at a normal, so then that strong base doesn't increase the pH. So it's kind of similar to homeostasis, where any stimuli that occurs will still bring ourselves back to the set point. So in homeostasis for the body, for example, if we're outside on a hot summer day, we sweat to maintain our internal temperature. And if it's a really cold winter and we're outside, well, we shiver so we can maintain our body temperature to generate heat. So sweating lowers our temperature, shivering increases our temperature, so then we can bring ourselves back to that internal temperature or that set point. And this is similar to buffers, where if we add some stimuli like an acid, strong acid, or a strong base, the buffer will bring that pH back to the set point, or at least very close to that set point, and resist any changes to that pH. Now, what is a buffer solution composed of? Well, buffer solutions are either a weak acid slash conjugate base pair, or they can be a weak base. So weak base slash conjugate acid pair. So we need at least a weak acid and conjugate base pair, or a weak base conjugate acid pair. Now the conjugate base, conjugate acid are very important in order for us to actually have a buffer. But another important thing is to have a weak acid or a weak base. If we don't have a weak acid or a weak base, then the solution will not be a buffer, and that solution will not resist changes to pH. If we have a strong acid, well, obviously our pH decreases, and if we have a strong base, our pH will increase to like 12 or 14, some very high number. So those are what buffers essentially are. They resist any changes to pH, and they consist of a weak acid conjugate base pair or a weak base conjugate acid pair. So what's an example of a buffer solution? And this is actually one that we've been talking about for quite some time, especially with the common ion effect video that we had. So this is going to be something like CH3COO, sodium acetate, and we're going to have CH3COOH, which is acetic acid, or I could just write it this way. So I'm going to have something like this. So this is our weak acid conjugate base pair. Now, as we know from our past videos, and as we know just in general, acetic acid over here is going to be a weak acid. The reason why is because this is not part of our strong acids. So I brought no clothes. Those are our strong acids, and because acetic acid isn't part of that acronym that we talk about, it is a weak acid. And over here, since we have a weak acid, this is going to be its conjugate base. Now, I might be wondering, well, why is it the conjugate base? If we remember from our past units, conjugate bases are going to be the, I guess you could say, precursors, that product after the weak acid. We know also that this is a weak acid, a Bronsted-Lowry acid, because it has donated a hydrogen. So essentially, you could just forget about this Na, because it's just going to dissociate into water, not really produce something, and this is what we're going to have. We're going to have that acetate ion. Now, I just put that Na, the sodium acetate, because that is the molecule that goes into water. But the sodium and the acetate will ionize from each other, and that is why we have CH3COO-, which is our acetate ion. And as you can see, we lost a hydrogen. when we lose a hydrogen, then that means that this guy over here is an acid, according to Lewis, or according to our Bronsted-Lowry acid theory. So this is going to be our conjugate base. Our acetate ion is going to be our conjugate base. So now that we know that, let's just say we added a strong acid to our buffer solution. So let's just say we added HCl. HCl is one of our strong acids because it's so I brought no clothes. That's the Cl part. So we have HCl plus, and we have CH3COO minus. Our acetate goes to our acetic acid. And like I said, we could just forget about this chlorine over here, because that chlorine is going to ionize out of the way, so we don't really need that. But if we actually wanted to write, we want to include water in here, we really don't have to, because usually in all of these solutions we assume that water will be there. But if we wanted to, we could just add water over there. Remember, water is in its liquid form. Everything else is in its aqueous form. So that's one of the reasons why we don't really put water in. We already assume that it's in water. So what we're gonna have is our chlorine over here and our acetate. So I'm just gonna take this water out just to make it look a little bit more simple. But just know that water is in the solution. So we're going to have our HCl, that strong acid over here. The Cl, the chlorine, has already ionized out, so we only have hydrogen. Our acetate ion, and when those combine, we have acetic acid. So if we add a lot of strong acid, then what's going to happen is these acetate ions will bind to the hydrogen to produce a weak acid. So then those hydrogens don't accumulate around and result in a lower pH. Because you have to remember, the reason why, or the way that we'd have a lower pH, is if we have a lot of hydrogens roaming around. So if we want to draw like a molecular diagram of this, then it would be something like, let's say, let me just copy this. So let's say we had a lot of hydrogens, and I'll just have it as like a blue over here. So we have a lot of hydrogens around here, and let me actually make these a little bit smaller just to make it a little bit more accurate. So we're going to have a bunch of hydrogens around here. And let's say we have a couple more. So we have a bunch of, let's just say we have a bunch of hydrogens roaming around. And this is in our buffer solution. So let me just copy paste this. So this is going to be our acetate ion over here. And I'll just color code this as red. That was a little bit too much of a circle. Let me do that. So this is our acetate ion right here, and it is a little bit big over here, but we'll just roll with it. So I'm gonna make it a little bit more over here, and let me do one more over here. So here is sort of a molecular diagram. Now this is not what the molecules actually look like. I'm just drawing circles and stuff just to represent what might actually happen. So what's going to happen is when we add HCl, the chlorines will just ionize from HCl. So what's going to happen is we're going to turn this HCl to H plus and Cl minus. We can forget about the Cl minus in this scenario. So we're just going to have those hydrogen ions, and these hydrogen ions are over here. Now what's going to happen is these acetate ions will bind to these hydrogen ions. So they'll bind to them and continue to bind to them, one acetate ion for each hydrogen. And what these will turn into is our acetic acid. So let me color code this green over here. So this is our acetic acid. So what's going to happen is this guy right here is going to turn into acetic acid. And let me copy that. And this guy over here will turn into acetic acid. This guy over here will turn into acetic acid. This guy over here will turn into acetic acid. As you can see, we've lowered the concentration of hydrogens. We only have like a couple of hydrogens. So that's showing, because we started out with, I'm guessing, we started out with like 8 hydrogens. So, and this is not like accurate sort of like numbering. Like, you don't want to think of it as we have the concentration of hydrogen. This is literally just showing how buffers work, in which the acetate ion are, we could say, conjugate base. Our conjugate base will, or we could actually say it is a weak base in this sort of scenario, but in our pairing that we talked about, our CH3COO minus is our weak acid, but nevertheless, the acetate ions are binding with the hydrogens to produce acetic acid, and this lowers the concentration of hydrogens to the point where there isn't a drastic change in pH. So let's just say our pH, and this is just, I'm just throwing out a random number over here, but let's just say, and this might not even be an accurate number, but let's just say that our pH starting out was 6, and when we added these HCl's, if we didn't have a buffer solution, then it might go to something like 2. But since we have a buffer solution, and because we have those acetate ions binding to those hydrogens, then our pH is going to be somewhere, is going to change to like 5.8 or 5.7. So it still is a little bit of a change, but it's not that significant to the point where this becomes so acidic, because we have those acetate ions binding to those hydrogens, lowering the concentration of the hydrogen ions, and that is how we maintain our pH. So buffers don't lower, or they don't lower pH in a significant amount, they don't increase pH to a significant amount. They lower it or increase it until we get to a balanced level, until we get back to our set point. That's all these buffers do. They just want to bring the pH back to normal. They don't really like all this havoc that these strong acids or strong bases are creating. And talking about those strong bases, here is what it would look like if we added a strong base. So that's COOH plus OH minus from NaOH. We're taking out the Na because we don't really need it. It doesn't really react to anything because we are in a buffer solution. Now, if we were in a salt solution, that might have been a different story, but since we are in a buffer solution, then we have that OH minus, and that is going to convert to our acetate ion, CH3COO minus, and we're also going to convert that to water. So over here is going to be our weak acid, because the weak acid is donating that hydrogen to that OH, creating water and creating acetate ion. Now that we know that, let's go through a practice problem, sort of illustrating how we could find pH with these buffer solutions. So let's just go back with our acetic acid and acetate ion sort of base pair, and let's say we have CH3COOH, or I forgot to put that other O. So OH, and we're going to have double bars, remember, because we are kind of adding both these reactions together, and also because this is a weak acid. Remember, weak acids don't fully ionize, and that is why we need to add these double bars, because it will be in equilibrium. Now, let's say if we had a strong acid or a strong base, now we just have one arrow, because strong acids and strong bases fully ionize, but over here, our weak acid won't fully ionize. That's why we have those double bars. And let's say we have something like hydrogen plus CH3COO minus, our acetate ion. So let's just say we had an initial, let's say, concentration of 0.1 molars of acetic acid and 0.1 molars of acetate ion, and it's asking us find the pH given those concentrations, and our Ka will be given, which we can say our Ka for these acetate ion acetic acid is usually going to be 1.8 times 10 to the negative 5. So we can set up our rice tables. Rice for reaction, ice initial, C is our change, E is our equilibrium concentration. So we're going to have 0.1, or let's say we had 1 molar, 0.1 molar, 0.1 molar, and we don't have an initial concentration for hydrogen. So if you want, pause this video and try to find the pH just with these numbers, giving your initial concentration of your acetic acid, initial concentration of your acetate ion, and your Ka. Now, as a hint, just remember that this is pretty much similar to how we found the pH compared to our past videos of having just a weak acid, weak base with the Ka. Alright, so if you did solve it, then our change in for over here for that acetic acid would be minus x, this would be plus x over here, our change in, so this would be 1 minus x, this would be x, 1 plus x. So if we write our Ka, which is going to be products over reactants, our reaction quotient, this is going to be x times 1 plus x over 1 minus x equals 1.8 times 10 to the negative 5. But we can assume that our change in is going to be negligible. Reason why is because we are in a buffer solution. So like we said, in a buffer solution, they resist changes to pH. So that's why we can say this change in is going to be negligible. Because with a buffer solution, our change in is going to be negligible. It's not going to change very significantly. So what we're going to have is x times 1 over 1, because we took out those x's, which is just going to equal x. And x is going to equal 1.8 times 10 to the negative 5. And because our x equals 1.8 times 10 to the negative 5, our x represents our hydrogen concentration. So what this means is that our hydrogen concentration equals 1.8 times 10 to the negative 5. And if we remember from our POH, pH sort of equations, we know that pH equals negative log of the concentration of hydrogen ions. So this is going to be negative log of 1.8 times 10 to the negative 5. And that gets us 4.74 as our pH. So biggest thing you want to realize when solving your pH with these rice tables is that your change in is always going to be negligible because we are in a buffer solution. Now, in our past videos on the acid and bases, we had that rule where it had to be greater than 0.5 molars and less than 10 to the negative 3, which still holds true. But just remember with buffer solutions that change in is pretty much going to be negligible because the buffers are going to resist a significant change in pH. So now that we got that done, now we understand how to find pH, let's move on to other questions concerning pH and if we added a strong acid. So using our same weak acid conjugate base pair, let's actually go through another question, but we're adding a strong acid. So let's just say we added 0.1 moles of HCl, our strong acid. Let's just say we added 0.1 moles of HCl, and we're still going over our scenario where we have CH3COO minus plus H plus goes to CH3COO H, our acetic acid, and we start off. So our initial was 1.0 molars over here, 1.0 molars. But see, now we have a concentration for our HCl, and we'll just say, because this is moles, so we'll just say it's in 1 liter, so it's just be 0.1 over 1, so this would be 0.1 molars. If you remember, molars equals moles over liters, so that's why we just put 0.1 molars. Now, in this case, when we're adding a strong acid, our initial concentrations for that ice table will be when our hydrogen has reacted. So what this means is that we are going to subtract 0.1 from 1.0. So this would be after H plus. Now, you may be wondering, well, why are we subtracting this concentration from 1.0? Why can't we just use 1.0 as our initial concentration? Well, with buffer solutions, like we talked about, the acetate ion will react with the hydrogen. Now, to determine our pH, our change in pH, or whatever pH we get, we need to assume that this hydrogen has already reacted. We need to have our initial from that rice table be the reaction from that hydrogen. So it would be 0.9 moles after our hydrogen. This would be 0, and this would be 0.1 molars because the acetate ion has reacted with 1.0 molars of hydrogen ions. So we're going to have less of our acetate ion because it's been used up, it's been consumed, and this is going to convert into our acetic acid, which is what the acetate ion plus our hydrogen ion has converted to. So now these are the concentrations we can use for our rice table. So I'm just going to pull this out from here. Just to make it a little less confusing, let's just forget about all that stuff. And we have to go back to our equilibrium reaction. So here's the reaction we're going to have, and you might be wondering, well, why did we switch it up? Why isn't our acetate ion in the reactant side? Why isn't hydrogen in the reactant side as well? Well, we have a weak acid. Weak acids and weak bases must be in the reactant side, and the conjugate stuff must be in the product side. So that's one thing to keep in mind when trying to write these rice tables, is that our weak acid or weak base, whatever we have, has to be in the reactant side, because that is essentially what's reacting with water to produce our, or reacting with whatever we're in the solution to produce our acetate ion or the hydrogen ion. So because we're talking about weak acids, weak bases, and the double bars represent that they ionize but not fully. So this is why we need to put our weak acids and weak bases in the reactant side first, then double bars, and then put our hydrogen or hydroxide concentration, whatever we have. So now let's go on with this problem. So 1.1, our change in over here is just going to be minus x, over here plus x, so this is going to be 1.1 minus x, 0.9 plus x, this is just going to be x, and our Ka is similar to our past equation, which is 1.8 times 10 to the negative 5. So when we put this in our reaction quotient formula, it's going to be 0.9 plus x, parentheses, x, 1.1 minus x, and this is going to equal 1.8 times 10 to the negative 5. Like we said before, our x is pretty much going to be negligible, so our change in is going to be negligible for these acetic acids and these acetate ions. So all we can do is just sort of erase that over, and let me move this over here as well, and I can just take this out. So it's just going to be 0.9 x times 1 over 1.1. And when you do all the math, our x is going to equal 2.2 times 10 to the negative 5. And remember that this represents our concentration of hydrogen ions because our x is our hydrogen ions. So negative log of 2.2 times 10 to the negative 5 is going to get you, let me actually do that math real quick. So we're going to have negative log of that. So we're going to get, and I'm rounding over here, 4.66 as our pH. Or let me circle it over here. So our past pH with pretty much no strong acid, strong base, our initial pH was 4.74, and now when we added a strong acid, it barely even changed, 4.66. Now that is not significant to the point where it's going to be more acidic or more basic. It's not going to be more acidic compared to 4.74. So you can see that these buffers barely even change with the pH. They still do change, but not in a significant amount that you'd expect. So that is how you find your pH using buffer solutions. And remember, when you're trying to calculate your initial concentrations, always your initial concentrations for your finding your rice table as a whole, finding your pH, this is going to be after that strong acid or strong base is consumed. So that's one of the most important things you need to realize, is that this is after that strong acid, strong base has been consumed. Now, instead of doing all that rice table stuff, you could also use the Henderson-Hasselbalch rule. So that's pH equals pKa plus log of your conjugate base over your weak acid. So you could use the Henderson-Hasselbalch rule in order to find your pH. So if we're going back to our past example, our concentration of, and this is after we consumed the our strong acid, our our concentration for our conjugate base is 0.9. So our pKa is going to be 4.74. Reason why is because pKa equals our negative log of Ka. Negative log of 1.8 times 10 to the negative 5 gets us 4.74. So that is our pKa, and that's going to be plus log of, and we said that our conjugate base concentration was 0.9. Our concentration for our weak acid was 1.1. So we'll just put 1.1, and that equals pH. So all we have to do is just put this in calculator. So 4.74 plus log of, and we got 0.9 over 1.1. And that gets us, let me write this down, that gets our pH of 4.65. So although it's not the exact number as what have done with the rice table, it's still very, very similar. And more than likely on your exam, you're more than likely going to use your Henderson-Hasselbalch rule. Not only is it faster, but it also just produces the same number as if you did a rice table. So it's more effective to use the Henderson-Hasselbalch rule towards finding your pH. That is if you're given your Ka and all your concentrations. So, and let's just say we also wanted to find our pH if we added a strong base. So what would that look like? Well, if we go back to our example of the acetate ion, acetic acid, what's going to happen is our acetic acid is going to react with our hydroxide to produce our acetate ion minus plus water, but we can pretty much forget about water. It's in its liquid form. So, and if we go back to our, let's just say we had 0.1 molars, 1.0 molars, 1.0 molars. So same exact concentration as before when we were doing that strong acid, but we have a strong base this time. And what's going to happen is the CH3COH will be consumed because when we add because our acetic acid will react with hydroxide to produce acetate ion. This is going to be 0. This is going to be 1.1 molars. So all you really have to do is just identify if you're adding a strong acid, strong base, and write the reaction as if you're adding a strong acid, strong base. And remember, this is going to be your weak acid. This is going to be your conjugate base. And what we have here is our acetic acid has been consumed by this hydroxide to produce acetate ion, and we have more acetate ion than the acetic acid. So if we go back to our reaction, our Henderson-Hasselbalch equation over here, and I'll just go down over here, just give us more space. If we go back to our Henderson-Hasselbalch equation over here, then our concentration of our conjugate base will be 1.1. Our pKa still stays the same, so 4.74 plus log of, and this is going to be 1.1 over 0.9. That's going to be our pH, and if we calculate this, it'll be 4.74 plus log of 1.1 over 0.9. That gets us a pH, and I'm rounding over here. It's going to be 4.83. So still very similar in terms of the range, like 4.74, 4.83. Not that significant of a change. And as you can see, all we really had to do is just identify, well, which concentration is increasing, which concentration is decreasing. The acetic acid is decreasing, acetate ion is increasing. We still use the same Henderson-Hasselbalch rule, and that eliminates the whole hassle of which part of the reaction do I put the acetic acid, which part of the reaction do I put the acetate ion. Because if we follow the Henderson-Hasselbalch rule, all we really have to find is our concentration of our acetate ion, which is our conjugate base, our concentration of our weak acid, plug in the numbers, and that's pretty much how you get pH. Now, besides knowing if it's a weak acid or weak base, there's another way to know if the solution is a buffer. And it is that if when you do your conjugate base, So conjugate base over your weak acid, the concentration of those. If it is less or equal than 10 or greater than or equal to 0.1, then that means you have a buffer. Now you might be wondering, well, why does it have to be that specific concentration? Well, it's because our pH must equal our pKa plus or minus 1. That's the range that we can put our pKa in. That's the range that we can actually use the Henderson-Hasselbalch equation for. If it's like pKa and our concentration of conjugate base over weak acid is 2, well then we won't really be in a buffer solution because this will change the pH significantly. So this conjugate base over weak acid, if we pull up our Henderson-Hasselbalch equation over here, so this part over here, right here, this has to be less than or equal to 10 or greater than or equal to 0.1. The reason why is if we do log of 10, so let me do log of 10, that will be 1. If we do log of 0.1, that will be negative 1. So our change in for this part has to be plus or minus 1, which gives us this kind of range. And the reason why is because we can't have a significant change in pH or else this won't be considered as a buffer. So that's maybe one of the conceptual things you might have to know. But then again, as long as you have a weak acid conjugate base pair, more than likely it will be a buffer. If you're just given your weak acid conjugate base pair, it's like a multiple choice question giving you, let's just say something like HClO, and then you have ClO minus or something like that, and then you have NH3, then you have NH4 plus. Those are going to be buffers because these over here are your weak acids and these are the conjugate bases for those. So as long as you know that, then you know that this is going to be a buffer solution, and that's pretty much all about buffer solutions. So hopefully you guys understood what buffer solutions are, because the only thing in their essence, the only thing they are is that they resist changes the pH, and they bring that pH back to its set point, back to a normal point. And they can do that by either consuming hydrogen ions or consuming hydroxide ions, depending on what we add to the solution. So hopefully you guys learned something, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.